Welcome everyone. Today we are going to explore how mathematics powers the artificial intelligence systems we use in our everyday lives. We will look at four big ideas: set theory, linear algebra, statistical modeling, and applied mathematics, and show how much one plays a role in making computers think and learn. Think about how Netflix recommends a movie to you on a Friday night. Behind that simple suggestion is a whole world of mathematics working quietly in the background. By the end of this session, you will understand exactly what that math is doing and why it matters. This is your Professor Atif Reed Muhammad, University of the Cumberland, Kentucky, and the lecture series is Analytical Methods for Machine Learning, PhDAI 731 series. This is the first lecture. Before we dive in, let us take a moment to understand what we are here to learn today. We want to build a clear picture of how mathematics connects to real artificial intelligence tasks, from sorting emails into folders to recognizing your face when you unlock your phone. Imagine you are a chef learning to cook a new cuisine. You first need to understand the basic ingredients before you can combine them into a great dish. In the same way, today we learn the mathematical ingredients so that by the end of this lecture, you can see the full recipe that makes AI work. So set theory and linear algebra is understand principles of set theory and their applications in data classification and clustering. Master vector and matrix operations for machine learning and deep learning. Apply linear algebra to understand neural network transformations, explore eigenvalues, SVD, and PCA for dimensionality reduction. I would suggest you look into SVD and PCA at Google Scholar or IEEE Explore. Statistics and applied mathematics. Grasp statistical modeling for building predictive AI systems. Understand Bayesian thinking and probabilistic reasoning in artificial intelligence. Apply optimization and calculus to training algorithms. Connect applied math concepts to real-world artificial intelligence implementations. We begin with the oldest and simplest ideas in mathematics, the idea of a set. A set is simply a collection of things that belong together. You use this idea every day, or every single day, I must say, without even noticing it. Think about your wardrobe. Your winter clothes from one group and your summer clothes from another. When the weather changes, you decide which group of a piece of clothing belongs to. That decision does not be contained in a box. It says, does this item belongs here or not, is exactly what set theory is all about. And it is the very first thing a computer must do when it tries to understand the data. A set is a well-defined collection of distinct objects, which are the elements. In artificial intelligence, sets represent data classes, feature spaces, and rule conditions. Set membership: element X belongs to a set A is denoted X belongs to A. This is the basis of classification. Does a data point belongs to a class? Well, that's a good question to ponder upon. Subset relationship: A belongs to B or A is a subset of B means every element in A is also in B, used in hierarchical classification and ontologies. A set is a group where every member clearly belongs. In artificial intelligence, a set might be all the photos that contain a cat, or all the emails that ran through in terms of spam. The computer's job is to decide for any new piece of data whether it belongs inside that group or outside of it. Imagine a school librarian sorting books into shelves. The shelf labeled science holds only science books. When a new book arrives, the librarian asks one simple question: does this book belongs on the science shelf or not? That yes or no decision is what we call set membership, and it is the foundation of how AI classifiers work when they label data. So universal set U, all possible elements in a given domain, the complement or A raised to the power C is equal to the universal set, where A defines what does not belong to the class. Cardinality is written like that: number of elements critical in measuring dataset size, class balance, and sampling strategies. Power set P of A, all possible subsets of A underpins combinatorial feature selection and ensemble methods design. Set operations in data classification. The set operations are union A, union B. So union technically is A union B. All elements of in A or B, merging features, sets, combining training data sets, ensemble predictions. Intersection is A, intersection B, elements in both A and B. It's technically finding common patterns, multiple label, and conditions. The difference A between A and B, elements in A but not B, anomaly detection, exclusion filtering, symmetric differences A, delta B, elements in either but not both, detecting misclassified regions. AI applications, decision boundaries and classifiers implement set membership implicitly. Classify X is equal to A if X is within the region A. Rule-based AI if feature 1 is within the high set and feature 2 is within the medium set, then the class is positive. K-mean clustering, each cluster CK is a set. Points are assigned to the set whose centroid is closest. Bloom filters, probabilistic set membership testing, used in database and caching layer in ML pipelines. So once we have sets, we can do things with them. We can combine two sets to get everything in both, find what two sets share in common, or take away one set from another. These operations sound simple, but they are incredibly powerful in artificial intelligence. Picture a hospital sorting patients. The doctor might want to find patients who have both high blood pressure and high cholesterol. That overlap people who belong to both groups at the same time is called an intersection. A computer does exactly this kind of thinking when it uses multiple conditions to decide whether a loan application should be approved or rejected. Fuzzy set theory beyond binary membership. Classical sets. Membership is binary. An element either belongs 1 or does not 0. Real world is rarely this crisp. Fuzzy sets are Zadeh in 1965 came up with the discussion. Membership degree mu, where A of X is within 0 or 1. The data point can partially belong to a class. The example here is mu, tall person is 0.85, a person is 6 feet and 1 inch is 85%, a member of all of the tall set. Fuzzy logic in AI enables nuanced decision making. With linguistic variables, temperature is very high. Speed is somewhat fast. Fuzzy clustering is FCM. With fuzzy C-means, each data point has fractional membership across multiple clusters, capturing overlapping categories naturally. Applications, medical diagnosis, symptoms partially matching multiple conditions, NLP sentiment scoring, autonomous vehicle speed control, anomaly detection with soft boundaries. Let me reiterate by sharing the applications with you: medical diagnosis, symptoms partially matching multiple conditions, NLP sentiment scoring, autonomous vehicle speed control, anomaly detection with soft boundaries. Real life is rarely black and white. Most things exist on a scale. A glass of water is not simply cold or hot, it might be warm or slightly cold or very hot. Traditionally, set theory only allows yes or no, but fuzzy set theory allows the computer to say somewhat yes or mostly yes. Think about a doctor's diagnosing a patient. A fever of 103 degrees is clearly in the high fever group, but a temperature of 99 degrees sits somewhere in between. Fuzzy set theory lets an AI medical system say this patient is partially in the fever group, which leads to a more careful and realistic diagnosis instead of snap judgment. Set theory applied k-means clustering. Now we see the set theory in action with a real algorithm called k-means clustering. This algorithm takes a large pile of unorganized data and automatically sorts it into groups so that items within each group are more similar to each other than to the items in other groups. Imagine a supermarket manager who wants to group customers based on their shopping habits. Customers who always buy organic produce end up in one group. Frequent snack buyers end up in another, and budget shoppers from third group. The computer does this automatically by looking at purchase patterns, and the result is set to distinct customer groups that the marketing team can target for personalized offers. So you just have looked at that. K-means partitions the data set X into K disjoint sets clusters. A direct application of set theory's partition concept. You can apply this, by the way. Okay, now we move into linear algebra, which is the mathematics of directions, distances, and transformations. If set theory tells us what group something belongs to, linear algebra tells us exactly where something sits in space and how to move it around. Think of a GPS navigation system. Your current location is a point in space, and your destination is another point. The directions of GPS gives you description how to move from one point to another, and the movement described precisely with coordinates and directions is exactly what vectors in linear algebra capture. Every piece of data in machine learning system is stored and processed as a vector. A vector is simply a list of numbers that describes something where it is, what it looks like, and what it means. When two vectors are very similar, it means the two things they describe are also similar. Measuring that similarity is at the heart of many AI tasks. Think about a music streaming service like Spotify. Every song is described by a long list of features: tempo, loudness, energy, danceability. Your listening history is also stored as set of such lists. When Spotify recommends a new song, it is finding songs whose feature lists are very close to one you already love. That closeness is measured using the mathematical operation called a dot product between vectors. When we organize many vectors together into a grid, rows and columns of numbers, we get a matrix. Multiplying matrix together is how a computer applies a series of transformations to data all at once. This is one of the most important operations and in all of machine learning. Think of a camera taking a photo and applying a filter. The original image is stored as a grid of color, values a matrix. When you apply a blur or sharpen filter, the computer multiplies that image matrix by another matrix that represents the transformation. Every Instagram filter, every camera beauty mode, and every face detection system uses this exact same idea of matrix multiplication working on image data. So the sparse matrices have feature representation as text TF-IDF. We'll be discussing that in length. And graphs are stored as sparse matrix, huge memory savings in production AI systems. So sometimes data has hundreds or even thousands of features, and most of them are redundant. Principal component analysis, or PCA, uses a mathematical concept called eigenvalues to find the most important directions in the data and throw away the rest, making the data much smaller and easier to work with. Imagine you are describing a person using 100 different measurements: height, weight, arm length, leg length, neck size, and so on. Most of these measurements move together. Tall people tend to have longer arms and longer legs. PCA, or principal component analysis, finds those underlying patterns and compresses all 100 measurements down to just a handful of key dimensions that still capture most of the useful information, like overall body size and proportions. A deep neural network, which powers things like voice assistance and image recognition, is at its core a very long chain of matrix multiplications. Each layer of the network takes the output from the previous layer, multiplies it by the matrix of learned weights, and passes the result forward. Think of a factory assembly line. At each station, a worker takes a partially built product, adds something to it, and passes it to the next station. In a neural network, each layer is a station, and the matrix multiplication is the work being done at the station. The raw input, say a photo of a dog or a cat, enters at one end, and by the time it has passed through many stations of matrix transformations, a label like Labrador Retriever or an orange tabby comes out to the other end. Now we enter in the world of statistics and probability. While linear algebra tells us how to transform data, statistical modeling tells us how to make educated guesses from data and how confident we should be in those guesses. Think about a weather forecaster. They do not know for certain that tomorrow, whatever the weather will be bringing us. But by looking at temperature patterns, wind speed, humidity, and historical data, they can say there is a 70% chance of rain. Artificial intelligence works the same way. It does not deal with certainties, but in carefully calculated probabilities, and the statistical modeling is the toolkit that makes those calculations possible. A probability distribution is a map that shows us all the possible outcomes of something and how likely each one is. Different kinds of data follow different shapes of distribution, and choosing the right one is essential for building an accurate model. Think about the height of adult man in a country. Most men cluster around an average height, with fewer men being very short or very tall. If you drew this as a graph, it would look like a bell curve. This is called normal distribution. An AI health screening system uses the same bell curve idea to flag patients whose measurements fall unusually far from the average, which might indicate a health condition worth investigating. Bayesian reasoning is the art of updating what you believe when you receive new information. You start with a prior belief, you see some evidence, and you update your belief to form a new, more informed conclusion. This is exactly how a good detective thinks. Imagine a spam filter for your email. At first, the filter has general idea that some words like free money tend to appear in spam. When it sees your specific emails over time, it updates its beliefs based on what you actually mark as spam versus important. The more evidence it collects, the sharper and more personalized its judgments become. This continuous updating process is Bayesian learning in action. So Bayesian linear regression is instead of point estimates, infers a distribution over weight W, provides uncertainty estimates alongside predictions critical to safety critical artificial intelligence. Bayesian neural networks or BNNs weights are distributions, not scalars, enable epistemic uncertainty quantification. The model knows what it does not know. Variational inference or MCMC and MCMC. Practical algorithms are variational in autoencoders or HMC to approximate complex posterior distributions at scale. So, you since you are in the PhD in artificial intelligence, you definitely have crossed through in your academia the statistics and the mathematics at a level in undergrad or grad that has given you the ideas of probability distribution and the use of statistical regression and classification methods. So the Bayesian method's reasoning uncertainty allows us to make decisions as sort of an informed decision. So the statistical regression and classification models, the regression models try to predict a number and classification models try to predict a category. Both are built on statistical foundations that tell the computer how to learn a pattern from historical data and apply it to the new cases. Think about a bank deciding whether to approve a home loan. The bank looks at hundreds of past customers, their income, credit history, existing debt, and whether they eventually repaid the loan or defaulted. A logistic regression model learns from all those past examples to draw a line separating likely repairs from likely defaulters. When a new customer applies, the model places them on one side of that line and gives the loan officer a recommendation. So the classification models given on the slide is support vector machines, Gaussian naive Bayes, decision trees, random forests, model selection via AIC-BIC. So I would suggest you to look into AIC-BIC by conducting a research on Google Scholar or IEEE Explorer. Now we come to the engine that actually trains artificial intelligence systems, optimization. The goal of training is to find the best possible settings for a model that it takes the fewest mistakes. Calculus gives us the tools to find those settings systematically. Think about hiking in the mountains and trying to find the lowest valley. You look around at the ground under your feet, figures out which direction slopes downward most steeply, and take a step in that direction. Then you look again and take another step. You keep doing this until you reach a valley floor where no direction goes lower. This process of always stepping downhill is called gradient descent, and it is exactly how an AI model learns from the data, where theory meets the practice, and algorithms that train AI systems to learn from the data. Gradient descent works by measuring how wrong the model currently is. This measurement is called the loss, and then adjusting the model settings just a little bit to reduce that wrongness. After thousands of such adjustments, the model becomes very accurate. Imagine teaching a child to throw a basketball into a hoop. After each throw, you give the child feedback. Throw a bit higher. Aim slightly more to the left. Each small correction moves the child's technique closer to perfect. Training an AI model is the same process. After each batch of examples, and algorithms give the model tiny feedback corrections, and over many rounds of practice, the model gets better and better at its tasks. So you also look at momentum, adaptive methods, or known as ADAM, and convexity. I strongly suggest you to look into the Google Scholar. That's what people have been looking into and working on these topics. Backpropagation is an algorithm that figures out exactly how much each part of neural network contributed to a mistake. It does this using chain rule from calculus, which lets us trace responsibility for an error all the way back through every layer of the network. Think about a restaurant where a dish came out badly. The head chef investigates and works backwards. The sauce was wrong because the sous chef over reduced it. And the sous chef did that because the prep cook gave them the wrong amount of liquid. By tracing backward through each step, you find exactly where the error occurred. Backpropagation does this same backward tracing through every layer of the neural network to figure out which weights to adjust and exactly by how much. So this is something that I thought to share with you. You can actually literally run this code. PyTorch AutoGrad automatically applies the chain rule across all operations, computing exact gradient for every parameter in the network. So unifying all pillars in all pipelines of artificial intelligence. Now we can see that all four ideas came together in a single real artificially intelligent system. None of them works alone. They are four ingredients in one recipe, and a good AI engineer needs to understand all of them to build something that works well. Think about building a self-driving car. Set theory defines the categories of car must recognize: pedestrian, traffic light, stop sign, and some things in similar line. Linear algebra stores the camera image as a matrix and transforms it through the neural network. Statistical modeling gives the car probability that an object ahead is a child crossing the street. An optimization powered by calculus trained that entire system over millions of miles of driving data until it becomes reliable enough to use on real roads. Today we covered a lot of ground, but the core message is simple. Mathematics is not just abstract theory. It is the practical toolkit that makes every AI system possible. From the voice assistant to your phone on your phone to the algorithms that detect cancer in a medical scan, the best way, next step for you that you can take is to start experimenting with these ideas in code. Pick any real data set, perhaps the prices of houses in your city or the reviews of restaurants you like, and try applying each of these mathematical tools to it. The moment you see the code run and produce a real result, these concepts will stop feeling like theory and start feeling like superpowers you actually own. Happy learning. See you in the next lecture.